An average rate of change. Is the simple process of calculating the rate of which your y values change compared to your x values. So sometimes you travel a certain distance. If you would go 200 kilometers in 2 hours, your average rate of change was 100 kilometers per hour. Which seems pretty good on a highway, but if your average rate of change is 100 kilometers per hour, that means you were probably speeding during some of it, because you can't just get into a car and say go and immediately be at 100 kilometers per hour and not stop at any stop signs. So if you did average 100 kilometers per hour, there would have been some time in there probably that you were speeding, unless you started counting while you were already on the highway and were driving on a highway with no stops for 200 kilometers, then that could be possible. See, it's there. When is that actually possible? After Brandon, because I think Brandon has some stop signs, and yeah, but then from Brandon, I think you have to slow down in Verdun. Okay, sorry, just probably possible something. So we divide the change in y, so in my case it was 200 kilometers, by the change in x, which was 2 hours, and you can figure that out. But you could use a slope formula for this. Because what that actually is your change in your y values divided by your change in your x values. Have you ever seen a little triangle for change? Awesome. So that's change of y over change of x. Your second y value minus your first y value, your second x value minus your first x value. And if your second x value was b and your first x value was a, then the bottom would be b minus a. And the top would be plugging into your function whatever b was. That would be your y value when you plug in b. And plug in a, that would be your y value when you plug in a. So these are all the same idea, just with different values. And the little triangle is actually a delta. So delta x and delta y. Now what this means for us if we were looking at a graph, since we're looking at slope, what you're finding is the slope of a secant line. So that's probably, trying to think, would you have in grade 9 in your circles unit, if you did that unit, which you might not have, because it was very popular to skip when you guys were in grade 9. You might have learned what a secant line is, and you might have learned what a tangent line is. But any 2 points on a graph, any straight line that goes through those 2 points is called a secant line. And so if you have a secant line, you can find the slope of that line by just doing the change, rise over run, change in y over change in x. Oh, and there is a little spelling mistake on yours. I need to make a new pen. Is this right? Yes. Oh, nice. I like to make a whiteout pen because there's supposed to not be an E on the end. And then we get this closer to our calculus that we were doing before. So we have the slope of our secant being f of b minus f of a over b minus a. Now, if we call the distance from A to B, if we call that distance h, then the value of B would just be A plus h. Okay? And I could replace the B with the A plus h, and then the distance between A and B is h, I could replace the B minus A with just h. And this, when we were practicing our skills with function notation the other day, we called that the difference quotient, which is going to be really important for calculus. So what we're doing right now is we're just developing skills that you've had in grade 12, grade 11, grade 10 pre-calculus, stuff you already know, and sort of playing around with those skills, but leading you towards some of the ideas of calculus. So if you had 3x squared, which is a parabola with 0, 0, it would have 1, 3, and negative 1, 3. I guess way up there it would have 2, 12, right? So if you drew a secant line home, and then even farther up, it would have 3, 27. If you drew a secant line from 1 to 3, what would the change of y be? What would the change in x be? And f of 3, we already said was 27. F of 1, we can see from our little graph, is 3 divided by 2. There's a picture of that graph again. The average rate of change is 12. Now we have no units here, so we can't say meters per second. We don't know what the graph was representing, but if there was units, you'd be expected to have units with your question as well. Now, if you went from 1 to any value other than 1, then we could say what our change of y is and our change in x. But we just can't calculate a number for the bottom because we don't know what x is. Now, since we know the equation of f of x, we could write 3x squared in for f of x, and we know that f of 1 is 3, so we would have 3x squared minus 3. And that is a right answer. But if it was a multiple choice question, that answer might not show up as your answer for multiple choice. So you do need to know how to simplify. The other day I said, if it was a long answer question, you are perfectly fine at not simplifying at all. You don't have to do any algebra. Even 1 plus 1, you can I'm going to leave it. I'm not going to let them know that I know the answer to this. I'm not going to reveal my hand early. I can leave 1 plus 1 as a final answer. That would be, some of you that would be very hard, right? Do you think you could just stop? Do you think you'd just naturally write 2? I think you would probably just naturally write 2. But if it's multiple choice and this doesn't show up, we might have to simplify. So you can see, I could factor to the top. I could factor out a common factor of 3, leaving x squared minus 1, which is a difference of squared, which is x plus 1 and x minus 1, and then my x minus 1s cancel out. And I get 3 times x plus 1, or 3x plus 3. And if that was the multiple choice answer, that's quite different than what you started with. So there is a lot of that on the exam, where you get one answer, but it doesn't quite match up, so you have to do some algebraic manipulation to make it work. Okay, and don't feel like it today. Maybe I'll get it all ready for tomorrow. But do you see at the bottom of the page, it says practice. Okay, tomorrow I'll give you your textbooks. And you can take them home. You don't need them, we're not going to be, if we're going to need them during class time, I will let you know ahead of time So you can bring them. But for the most part, you can have them at home to do practice questions at home. Okay? Generally, what ends up happening, I would say, in this course, is we give you lots of take-home quizzes that keep you busy, and you find that you don't necessarily get all the homework questions done. But that'll be okay because you do more than enough questions with take-home quizzes and pre-quizzes. So what I'm saying is if you don't get all the homework done, you don't have to feel guilty. Not that any of you have ever felt guilty for not doing homework. I don't think that's a thing anymore. Okay, so we're going to review functions that you've graphed and know, and then we're going to add some new ones in here. For example, the constant functions. Those are ones that are just equal to some number. Like this one might be, this red graph might be y equals 3. They're horizontal lines. Y equals 7 would be a horizontal line at 7. These are called constant functions because the y value is always the same. It never changes. The domain is everything. It's like, there isn't even an x in there. Is there any x values that are not allowed? No, you can. Like, y is equal to 3. Solve for y, which is always 3. Solve for y when x is 2.738. It's still 3. Right? It's a constant function. It's always 3. There's no x even involved. The range then is just a single value. If it was y equals 3, your range is just 3. So you can just write just a number. Or sometimes people write it just like this, y equals a. There are no x-intercepts unless it's on the x-axis, in which case there would be an infinite amount of x-intercepts. And there is a y-intercept. It is exactly the value. So there's our constant function. Really easy, really boring. There is the identity function, which is a special kind of line. The identity function is just when it's equal to itself. It's like, who are you? I'm myself. What's y when x is 3? What's y when x is 1? Right? So you are always equal to yourself. That's why it's called the identity function. Domain and range are everything. X-intercept and y-intercept are 0. You are yourself and you are a bit odd. Yes. So the identity function is an odd function. Remember, odd function was symmetrical in the origin or a double flip and you match up with what you had before. So can you see if I take the top right hand corner and flip it over this way and then flip it down, it matches up to the bottom part. So it is an odd function. Okay. Also, please, sometimes I get excited about the next slide and I don't have to write anything down like you have to write things down. So sometimes I will go too fast because I'm like wanting to get, the next thing is not that exciting, y equals mx plus b. But if that happens, you just let me know. Mr. Jarrett, can you just go back for a second? I was waiting for someone to say, can you go back to yesterday at about... So here's our y equals mx plus b equations, where m is your slope. And you remember that positive slopes went up from left to right? Negative slopes went down from left to right? No slope are our constant functions. Does it make sense? With no slope, if you put a 0 in, you just get a number, which makes that constant function from before. Power functions. X squared, x cubed. the 4, x to the 5. So we're going to start off with the power functions that are odd. And all the odd power functions are odd functions. Domain and range for all of them are everything for an odd function. X-intercept and y-intercepts are 0 for all the odd functions. And after 1, like x cubed and x to the 5, we're going to find out later that at 0, 0, and these graphs really show it probably more like, I would say a bunch of you made small, tiny mistakes in grade 12. Because when you graphed x cubed in grade 12, you probably did this. And you lose no marks for that. That looks, for grade 12, that looks perfectly fine. Okay? But technically, there's a problem with my graph right here. Technically, it's supposed to flatten right out at 0. And if you think back to your polynomials unit in grade 12, do you remember when we would say like a 0 has a multiplicity or it happens 3 times or 5 times, and that the graph had to flatten out at that point? The problem is you learned the x cubed graph before you learned that other graph. And so you probably drew it like this a lot of times. But it technically should flatten out completely at that point. And as you go higher with odd functions, it's just like flattening out. If the x to the 7 flattens out faster, the x to the 9 flattens out even faster at those points. And then our even ones, there the range is always greater than or equal to 0. And you can see how they flatten out more and more and more as well. Awesome. Reciprocal functions. Now, part of this goes back to grade 11. That was the first time that you did reciprocal graphs, and you also did it again in grade 12. A reciprocal function, the standard one is just 1 over x. But you learned how to graph 1 over everything in grade 12. It has some asymptotes. So the best and easiest way to write domain and range is just to write what it can't equal. There are no x-intercepts and there are no y-intercepts. But again, it's an odd function because if you do the double reflection, it matches up perfectly. There, see that noise? That's me getting excited about the next one because I know that you've done square roots before, but I don't know if you have graphed a cube root before. No? It's kind of fun. So this might be a new graph for you. Root functions, right? Cube roots, nth roots, square roots. It's a little reminder of like grade 9, grade 10 math, that you can write a square root as a rational exponent. Do you remember that? So I can either write the cube root of x or I can write x to the 1/3. I can either write the square root of x or I can write x to the 1/2. And we're going to be switching back and forth between those things quite a bit. So that's going to be really helpful to remember. Now your square root graph, you've done that one before. Domain and range are both 0 to infinity. Now we use square roots algebraically to undo squares, right? And whenever you have something that sort of undoes something else, that's an inverse of each other. Something that undoes something is an inverse. We're going to have a whole section in this unit about inverses, but just a little reminder of inverses. In grade 12 math, graphically, what did you do to points with inverses? You switch the x and the y values, right? And graphically, that's like flipping over the line y equals x. Now technically your square root graph is perfectly half of a parabola. But the square root graph doesn't have that bottom green part of the parabola because you're not allowed to square root negative numbers. So you can only take part of the parabola when you flipped it. But with cube roots, you're allowed to cube root negatives and cube root positives. Just like you're allowed to cube negatives and you're allowed to cube. Well, yeah. But the cube root graph, can you see the x cubed graph kind of on its side? Because if I took an x cubed graph, nicely flattening out there, and I flipped it over y equals x and switched my x and y's, I would get this point, and this point would stay the same, flipped over, or this would be like this. We get this shape. So if you switch the x and the y's of an x cubed graph, that's the graph you would get, and that's your x cubed graph. So your x to the 4 graph would be similar to this one, x to the 5th root graph would be similar to that one, and so on. Here are your domain and range, it's everything. And your x-intercept and y-intercepts are 0. Now I didn't reveal those boxes right away. Question, how many people had it already filled in? All right, good. Feel free to fill in things ahead of time. It wasn't very hard to fill in those things, right? Sometimes be careful when your brain is on like energy saver mode, where you just don't do any thinking during class until something shows up, okay? You want to have, I'll tell you that if you have your brain in active mode during class and you try to predict what's happening ahead of time, okay? That will actually get you to save time later on when you have to study. Because you're inadvertently, like you have to sit here anyways, right? You're going to be in class either learning or in energy saver mode. You get to choose. But if you put yourself in that learning mode during class, that is bank time that you won't have to spend extra time studying later. Which is really, like, it's like the hint for learning in class. Question?
The x and y values might be reversed.
The x,
For the ints.
the x-intercept you don't think should be 0 and this one should be
No,
0, they
the
should be
x in-
split, so this one should be 0 and this one should be 0?
No, like for the x int y equals 0, and for the y int x equals 0.
An x-intercept, you're always solving x for x. Like if this was my x-intercept right here, because it crosses the x-axis, and I counted it 1, 2, 3, it would be like at 3, 0,
Oh, yeah, right.
right? So we would be writing x equals. I can see why you're wondering, I know what you're trying to say there, but it does work out in this case. Okay, good. Absolute value function. This is the one that we could write piecewise. But Here is a way that I think you don't normally write your absolute value function. This is true. We did this in grade 11. Did you know that the square root of x squared is the absolute value of x? And in fact, it was one time that I was at a presentation by a university professor who was saying, if university professors could complain about a bunch of things that kids make mistakes on from high school, this was listed as one of them. That they didn't know that the square root of x squared is the absolute value of x. What do you think the number one mistake is? Just writing x. Why is that technically wrong? Well, the square root of 25 is not plus or minus, just 5. Have you ever typed square root of 25 on your calculator and it's told you anything other than 5? It is only 5. We have to be careful because if you're solving this is where you have your plus or minus. When you square root both sides of an equation, you have to add the plus or minus. Because this part right here is just going to be 5. So if you're solving that equation, the answer is plus or minus 5. However, a square root on its own is always positive. So then, what happens if I started with this? Order of operations would say, first you square the negative 5, and then you would get 25. And then the square root of 25 is 5, which is the absolute value of negative 5. Square roots always have a positive answer. Look at our square root graph that we just did. Right? There's your square root graph. It doesn't, I erased this green part. That is not there. Neither is that. Our square root graph as a graph is always positive. So the absolute value function can be written in three ways. Probably most used to it, seen it this way. Have to remember that the absolute value of x squared is this. Because it is possible for x to be negative, but then the answer would come out positive in the end. Or you can write it as a piecewise function. Domain and range and intercepts, easy. Domain is everything. Range is bigger than or equal to 0. Now some new ones. The floor function. The floor function is the largest integer less than or equal to x. It's got some weird things where it just draws little, like it has absolute values, but draws like a floor underneath it. So if you had 4.3, you would get 4. Some people could argue, that we should use the floor function when figuring out marks. So if you had an 88.8, your grade would be 88. Oh, there's some, no, I don't like that. Is it any different than what we're doing right now? Like right now, an 88.8 changes to an 89, right? We round up. But we still have a 1 unit rounding system. Anything between 88.5 and 89.49 becomes 89. That's our current system. We have a 1 mark range where everybody becomes an 89. It is somewhat arbitrary. We can make a new 1 mark system that, well, you would like this. We can make the new one. Everybody would like the ceiling one. Everybody be happy with the ceiling one. Your mark is 70.01. Your mark now becomes a 71. Wouldn't you like that one? Everything rounds up as soon as you hit that decimal place. And the graph is kind of weird because it's got filled in circles and open circles. So for example, here at 2, if you put in 2, it's 2. But if you get close to 2 on the other side, like 1.999, it's getting closer and closer, but you'd have an empty circle on that side. Because it's going to be completely flat, and then it jumps to the next one. So floor function of 1.9 would be 1. The ceiling function of 1.9 would be 2. Your domain and your range, well, your domain, still everything is included, but your range is just, and I've got the Z here for integers. What is the French word for integers? 1, 2, 3, positive, negative, whole numbers. What's that French word? Entier? Would that be, does that include the negative ones? I don't know. Because there's also in English we have whole numbers. Those are the positive ones. And when I hear entier, I think whole numbers, but maybe it's integers. Well, now I've got you thinking French. I'm sorry. You can think English again. But it also doesn't have the letter, does it, is there a French word with the letter Z? Why do they use for international symbol for integers? Why is it a Z? It actually comes from the German language. The German word for number is Zahlen, which starts with a Z. So that's why we've got that. These functions are called step functions because if you were wanting to walk up on them, it would work out very nicely, like little steps. Do you remember your polynomial functions unit in grade 12, where you did like graph x cubed plus 5x squared plus x plus 1. You had synthetic division and long division, a little bit of that. Okay, those were your polynomial functions. Now, this is the general form, which means you could have numbers in front. That's what all these little a things are. They could be numbers in front. And then you could have exponents that start with 1 and go down by 1 each time. Like x cubed functions could have an x squared, could have an x, and could have a number. Sometimes when we write things in their general form, it's just a way to try to be more confusing looking, but it's not really necessary. So don't worry about the confusing form. We will deal with regular numbers, okay? So our exponents are whole numbers, not negative, just positive integers, okay? The leading coefficient can be any number, and all the coefficients can be any number, but we call this first one the leading coefficient. You might remember that, like, whether it was positive or negative helped you draw the graph, right? Like a negative x to the 4 graph, you might have some weird stuff happening, but the ends would point down. A negative x to the 5 graph would have started up here and ended down here on the right. So we use that leading coefficient if it was positive or negative. And the constant term is also the y-intercept, because if you plugged in 0 for x, all the other stuff would go away, and you would just be left with that constant term. The constant function is a polynomial. Linear functions are polynomials. Parabolas, cubic functions. Right. Now that's what you did in grade 11. In grade 11 you did parabolas. Okay. This you probably don't remember, but if you took the b value and divided by 2 times the a value and made it negative, that's your axis of symmetry. The negative b over 2a technically is the x-coordinate of your vertex. So may. right? We learned that if it was positive, a leading coefficient was positive, it opened up. If it was negative, it opened down. And there's that new word for everybody coming from French. The max or min point on the parabola is called the vertex. The x-intercepts you could find by factoring, or the quadratic formula. If you want to use the quadratic formula in AP Calculus, you have to have it memorized. So one of the things that we're developing here is reviewing some of the stuff. Like, do you remember that formula? And then the inside of the square root part is called the discriminant, the b squared minus 4ac. And the discriminant tells us if your parabola has two roots, if your parabola bounces off and has one root, or if your parabola never touches the x-axis and has no roots. Because this plus or minus, if you add or subtract a number, you're going to get two different answers. Does that make sense? So when it's positive, you add or subtract a positive number, you're going to get two different answers. That tells you you have two roots or two x-intercepts. If it's equal to 0, adding and subtracting 0 ends up being the same thing. And then you only have one answer. But if it ends up being negative, you can't take the square root of a negative. That's not possible to solve. And graphically, that means you never have any x-intercepts. Do you remember the vertex form of the quadratic equation, quadratic function, where h and k are the vertex? And this is the roots form, where it's factored. Then p and q are your x-intercepts. Smiling because I'm watching patterns of different people using the big workbooks. Lots of you have brought the whole thing. Right? That's perfectly fine. But that means you're going to be carrying that vectors unit for 6 months that you don't need it. Some people, I see someone's taken it and stapled the unit together, right? But then they have to deal with the staple. Some people pop things out and write it outside, and some people keep it in the binder. So you can choose whatever works best for you. You might have a smaller binder that's just the current unit that we're working on. You might get nervous at the end of the unit that we might start the next one, so it's up to you. Okay, grade 12. We looked at new polynomials, degree 3, degree 4, degree 5, cubic, quartic, quintic. We talked about multiplicity. I mentioned that already with the x cubed graph. If multiplicity is 3, then it flattened out. If the multiplicity was even, then your graph bounced at that x-intercept. So we used our x-intercepts and their multiplicity and their end behavior to graph things. So if it's an even number, it touches but does not cross. It bounces off. And if there's an odd number, the graph crosses the x-axis and maybe if it's a 3, a 5, a 7, a multiplicity of 3, 5, or 7, we talked about it flattening out or it bending at that point. You might remember that from grade 12. Which means if you have a polynomial function in factored form, it becomes easy to graph. Okay? A couple of things in here. So the x-intercept of 2 has a multiplicity that's even, so it bounces there. The x-intercept at 4 has a multiplicity of 3, so it crosses but bends at that place. Bends or flattens out. If you multiply this out, do you see that you have an x to the 5 graph? Because the first squared thing would give you an x squared. The second cube thing would give you an x cubed. And an x squared times an x cubed would give you an x to the 5 graph. Which I always say odd functions act like lines. This would be an odd function with, it's a positive 1 out in front. A line with a positive slope starts down there, ends up there. Notice our graph started down here, ended up here. So when you have an odd function, they act like lines. Even functions act like parabolas. And that can tell you where the end behavior is. So if you knew this, and you knew bounce, and you knew bend, could you draw the whole thing? Yeah. You go up, bounce. Oh, I got to come back to this one. I got to bend, and then through. And that was enough for grade 12 pre-calculus. Okay. In AP calculus, we're going to figure that out. How low does it go in between? In grade 12 pre-calculus, you would get full marks for this question whether you went down this far. You would have been full marks if you would have made it do this. You would have got full marks if you would have been like, you had free liberty to make that minimum wherever you wanted. All of those would have been fine. I don't think very many people would have. That's a little extreme. You could have even got asked for extra paper on the exam and taped a whole bunch of papers and then made it go way down and then way back up, and they would have to mark it right. And you'd have to fold all those papers into your exam in the end. That would have been perfectly fine. But in calculus, we are going to figure out this minimum point. We're also going to figure out where the graph changes from being, we're going to figure out this point and this point as well. That's where the graph changes from being here. We would say the graph is sad. You know, it's like bent down. And then in this part here, the graph gets happy. We'll call that concave down and concave up. We're going to find out where it changes. That's some of the things that we do in calculus. But in grade 12, yeah, there we go. All of that would have been accepted. We're just worried about the bounce, the bend, and the end behavior. Oh, there was another one there, but I guess you can do that one on your own and check with your graphing calculator. What the heck? This is not your next page. Did my smartboard miss some stuff? Oh, I do have this next one. You don't have this at all, right? You do? Oh, it's in a different order. Oh, so we just skipped this earlier. That makes sense. Do you want it? You want this bothering you that you didn't know what this box was? No. That's the end behavior thing. We already talked about it in our example. Would have been nice to have in the notes before our example, but I guess that's why. So if they're even, this is where I think of parabolas, up, up, or down, down. Here's where I think of lines and their end behavior. So now I do have your next example. So, first of all, if you multiply this out for its end behavior, here I'd have an x squared, here I'd have an x cubed, here I have a -2, So it would be a negative 2x to the 5 plus dot, dot, dot. I'm not going to multiply it out completely. I'm just looking at that biggest power and whether it's positive or negative. And it's going to be negative. And since it's an odd function, I would think it acts like a line. So there's my end behavior, and sure enough, it's starting up here, ending down there. And it's already factored, so it's easy to see what our two x-intercepts are. And the odd one, it's going to go through but bend or flatten out. And the minus 1 has a multiplicity of 2. It's going to bounce. So you would have enough information to draw the bounce, draw the bend through. This point is really easy to figure out, your y-intercept, because all you have to do is plug in 0 for x. Plugging in 0 for x and doing some mental math will give us 16. So in grade 12 pre-calculus, you would have needed the end behavior, you would have needed all of your x-intercepts, you needed to label your y-intercept to draw your graph. Again, in calculus, we're going to figure out this point. %, of grade 12 students play connected odd. So when they draw this, they would have probably been here, hit a maximum there and come right back down. If this was on a final exam of grade 12 pre-calculus, they'd all get 100%, but 90% would do that. In the 10%, the other ones, some of them might have a little bit more accurate. Some of them in that 10% just did it completely wrong. That could happen as well. And so the tricky ones you would have had in grade 12 is where they gave you the graph. Oh. This is all right. I didn't miss any, did I? No, I think we're good. Trickiest ones is where they gave you the graph. Yes.
Yeah, you did miss.
I did miss one. Which one did I miss? I thought I was
What
following
the
along.
X?
I missed this one?
Yeah.
Oh. Did I do this one twice? I don't know. Okay. We're all good. Well, I don't. We're not good at all. Something is. It's. Oh, there we go. Smartboard is mimicking me by showing issues of delay. If you multiplied this one out, you'd have an x squared, an x, and an x. You would have an x to the 4, and it would be positive. So notice your end behavior. It acts like a positive parabola. The 0 has a bounce. The 3 it crosses. The negative 2 it crosses. Now in these first couple of examples, we had the equation and we drew the graph. And so in our last one, can you work backwards? If you have the graph, could you figure out the equation? And the hard part that you're going to have to deal with is this right here, this point. The number one close but wrong answer looks like this. y equals, or p of x equals, I guess, I'll go p of x. It's labeled as p of x. P of x equals, and they have a bounce. No problem getting that right. They have the bend. No problem getting that right. And it goes down from left to right, so they put a negative there. And that may or may not be right. Does it actually work? If I plug in 1 right now, do I get 6? No. So this is number one mistake. It's very close to being right, but there's a possibility and that this could be a -2, a -3, a -1/4. So how do we go and solve that? Well, we just put in that we don't know what A is. We don't know what that number out in front is. I know that it's negative because of my end behavior. But if I want to solve for something and I know it goes through the point 1, 6, I can plug in 1 and 6, do some mental math, and solve for A. Oh, -112. That was my next guess. No. Guessing might not be a good choice here. Because -112, I don't know how many that would be on your first chance of guessing. I guessed -1 first, I was wrong. Then I probably would have guessed -2 and still been wrong. So actually solving it is a better method, and there is the equation. All right, we'll look at rational functions tomorrow. I'll get your textbooks set up and ready for tomorrow.